All right, welcome back. So what we need to do is finish up and talk about that third material that we mentioned before. We're going to talk about body-centered cubic. And we can abbreviate this as BCC. All right. So we can draw this. This is cubic again. So we can draw that cube. We have our 1, 0, 0 pointing out of the board towards us. Our 0, 1, 0 direction pointing to the right. And our 0, 0, 1 pointing up. We're going to again start by putting an atom at each corner. So do that. And then we're going to put another atom right in the center. Okay? Right in the center of that body. So again, we can find common materials that have this crystal structure. So these would be things like iron in the phase that is stable at room temperature. Okay. This is called ferrite if you're really interested in this. But it could be other things like tungsten, vanadium, molybdenum, chromium, and tantalum. Now, like we said, with HCP metals, a lot of them are light. With BCC metals, a lot of them have very high melting points. So that's true of things like tungsten and tantalum. All right. So one thing you notice is we didn't say anything closed packed. In fact, this is not a closed packed structure. Okay, and it actually has a packing factor. So how much space is filled? Of 68%. So it's not a lot lower, but it's noticeably lower than the 74% that we saw for FCC and HCP. If you look at this, you will also see that any given atom, the easiest atom to pick is that one in the center of the body, only has 8 nearest neighbors. All right? So we only have the ones on the corners that are nearest neighbors, and that's fewer than we had before. We had 12 nearest neighbors for FCC and HCP. The difference, though, is that the next body-centered atom, the one above, the one below, so on and so forth, are relatively close. So it has another 6 second nearest neighbors that are relatively close. So if we draw a plane along the diagonal of this cube, we'll end up getting the closest pack directions. I'll draw that over here. So I'm saying that I want to draw the 1, 1, 0 type plane, and that would be something that goes diagonally across this cube. And the closest packed directions are going to be connecting that atom in the front left to the atom in the center of the body. All right? And that would have the direction A over 2, 1, 1, 1. And we'll say that we're interested in A over 2, 1, 1, 1 type directions. All right? So the first thing we can do is we can sort of just draw that plane. When we said FCC, we said, okay, the closest directions are from one atom to another, but then we ended up finding partial dislocations and other sort of paths we could follow. So let's see if we can get something like that in BCC. So I'm going to draw that 1, 1, 0 plane. All right. that little rectangle that I outlined here would be connecting these atoms. Now this would actually have a height of A and a width, this little rectangle, would be square root of 2 times A. Okay? So it's a little bit wider here than it is tall. And that close pack direction I just plotted would be like going from one site there to the next. That would be A over 2, 1 bar, 1, 1. If this is a 1, 1, 1, is the 1, 1, 0 plane. All right? So unlike the FCC, we don't see any obvious other paths we can take. You could, of course, dream of, well, maybe we could go back here to the left, up and over, but that's not really making a whole lot of sense here, okay? So that would definitely be a longer path. It would definitely be higher energy. So we don't have an obvious path for partials here. So what that tells us is slip is predominantly on the 1, 1, 0 planes in BCC. We do have one complication. It's that we have secondary slip planes. So in addition to this 1, 1, 0 type plane, we can also get slip on the 1, 1, 2 type planes and the 1, 2, 3 type planes, although it's less common, okay? And actually this usually happens if we really increase the temperature at which we're testing. So it seems simpler. There's no complication from partial dislocations in this case. But, of course, it's a graduate class. Never quite as easy as it seems at first glance. There is a complication with BCC materials, but it really has to do with one type of dislocation. It has to do with how screws behave. So, if we look down the line direction of an A over 2, 1, 1, 1 screw dislocation, we'll see something pretty interesting. So I'm going to draw my cube again to sort of get us oriented with how we're trying to look. I have my BCC structure. We're looking down the line direction, all right? It's a 1, 1, 1 type direction. That direction is connecting this back left atom to the front right atom, okay? We saw that when we defined the 1, 1, 1 plane in FCC. All right? So we're looking down that direction. And I want you to go to our website and grab a handout that I put on there for looking down the core of a BCC screw dislocation. It looks something like this. Okay? It has a bunch of little circles with arrows connecting them. Right? And on that figure, it's plotting where the atoms would be when we look down that direction. Okay? And the colors of the atoms correspond to different planes. All right? So, this atom at the front right corner of our material, a 1, 1, 1 plane there is colored white. The next 1, 1, 1 plane behind it, this one right here that I just drew, that's going to be gray. And then the next 1, 1, 1 plane behind it is going to be black. Okay? So we're drawing the atoms in a 1, 1, 1 plane for BCC. Okay? And what you see is that they're not falling on top of each other, right? They're falling in different positions in the plane of this piece of paper, which tells you that none of them are on top of each other, okay? So in this picture, the length of those arrows that you see give you the disregistry of the dislocation core. So what they're telling you is, where are my atoms displaced with respect to where they would be in a perfect lattice, all right? So the length of each of those arrows is going to be proportional to the difference of the 1, 1, 1 direction, or out of the plane in which we're looking, displacements of the two atoms. So each of those arrows is going from one atom to another, right? So if I look here, this arrow right here is going from a gray atom to a black atom, okay? So it's saying, as I go between those, how much am I pushed in and out of plane displacement, okay? So what you notice on this figure, and this top is option 1, this top is option 2. There are sort of two different ways you could see it, and if you think about it, you can see some trends, okay? The displacements are highest right at the center of the picture. That's good. But you can also kind of see these lines where the displacements are higher than they are in other places. So I drew a line through mine, so you can look at yours. And the bottom one, all it is it has those lines in a different configuration. It flipped the configuration 180 degrees. Okay? So the fact that you have these lines going off in different directions with higher displacements actually tells us that something interesting is happening. Okay? When we first derived what the stress and strain field of the atoms around the dislocation would look like, we came up with something saying that they should be displaced in a way that's 1 over r. So the amount you're displaced from the perfect crystal should be really high near the center of the core, and as you get further away, it should get smaller. But that 1 over r also means that it should be radially symmetric. So you would expect it to be at a given distance r, but the angle's changing as we move around there, we would see the same displacement. And that's not true. That's not what we see here. Okay? So you're actually getting displacements concentrated onto different planes. And these displacements are actually concentrated on 3 intersecting 1, 1, 0 type planes. Okay? So, we have a situation where we're having some sort of dissociation of our dislocation core from the perfect case. All right? We're actually going from, what we have is a over 2, 1, 1, 1 type dislocation is actually spreading into 3 different cores, one along each of those planes. And each of them is going to be an A over 6, 1, 1, 1 type direction. Okay? So we have 3 of these. So how would we figure out what's preferred? We would look at the strain energy, right? And again, we're doing the same thing we saw with our other crystal structures. This is a full dislocation. These other new types of dislocations are called fractional dislocations. So they're kind of like partial dislocations, but they're a little bit different. They're not remaining on the same slip plane and things like that. All right? So if we go and we calculate what the magnitude of b squared is for each of these cases, we'll get that it's 3/4 a squared for the full dislocation case. So that's our strain energy penalty. But it's going to be 1/4 a squared for those fractional dislocations. So it's much lower for the fractional dislocations. Those are preferred energetically. All right? So this process is kind of wacky and a little bit hard to visualize, but it's something called threefold splitting. So we have a dislocation that doesn't break into two, it breaks into 3 fractional dislocations. And the really important thing is it gives us a 3-dimensional dislocation core. So we now have, if you look at where those 110 type planes are, they're coming out of the page that you're looking at in this figure at different angles. They're not all parallel to each other, okay? So that means that these new dislocations that we have up here are all in different directions. We have a 3-dimensional core. And kind of like we saw with our partial dislocations in FCC, we said that those partials need to come together before we cross-slip. We have something similar, but it's even a bigger deal here. So these fractional dislocations must recombine before the dislocation can even glide on its original slip plane. So if you want to think about it, in FCC we were saying, well, the secondary type of thing where we move off onto another slip plane is a little bit harder. Now we're saying even the basic thing, just going along the slip plane that I started on, becomes a lot harder. All right? So this gives us the result that the velocity of screw dislocations is much, much lower than the velocity of edge dislocations in BCC materials. Okay? So this is a complication associated with the screw. It's really hard for them to move. And this is that sort of velocity dependence on dislocation character that we talked about. And what this means is that these screw dislocations are rate limiting. Okay? So if I draw a dislocation loop, its Berger's vector was this. These ones on the top and bottom are going to be screw dislocations. They're going to have a really small velocity. I'm going to represent that with this arrow, compared to the velocity of the edge components. So if I take this thing that started out as a circle, and I look at it at some later time, what I'm going to find is that it's now very elongated. So it hasn't moved that much up and down, but it's moved a lot right and left. And I'll even make this bigger to accentuate this. Right? It's really stretched out. So it turns out that that has a large impact on how these things even move. What's the mechanism through which they move? So you can think about dislocation moving in 2 different ways. We could say this screw dislocation at time 1, this top part right here, it wants to move up 1 step. So one option is it moves up 1 step by time 2. But that means that along this whole length, it needs to recombine and move up. Okay? So, alternatively, let's think about this dislocation at time 1. What if just one little local area changes? What if at time 2, we look largely the same, but just one little piece has recombined and moved? What would that look like? So there'd be an energy penalty, sure, but it's a relatively small one. But now what we have is that screw, which is slow, and these 2 new sides, which are edges. And those can move really fast. So these things can unzip really fast And then at time 3, my dislocation has taken that same step forward. But it requires this intermediate step, okay? And this is called double kink nucleation. And it's very dependent on temperature, right? So this is going to have some real consequences for our materials. So what we want to do real quickly is I want to compare FCC and BCC and see if we can connect these little funky details about how individual dislocations move to our overall behavior, okay? So in FCC, we had a Berger's vector of A over 2, 1, 1, 0. But we had Shockley partials. So our full dislocation would dissociate down into this partial set of partials separated by a stacking fault, which had the effect that these could glide easily, but this can lead to more strain hardening. And we saw the formation of dislocation locks, weird things happening with cross slip and stuff like that. So BCC materials, on the other hand, so they have a Berger's vector of A over 2, 1, 1, 1. But instead of these Shockley partials, we end up getting these fractional dislocations. That's the complication. And you can think of it as some sort of threefold splitting off onto different 1, 1, 0 type planes. Okay? And the main effect is that screws are harder to move by glide. Okay? And you know what you see here is that the yield stress, sort of the effect of each of these things, is for BCC, because it's harder to move dislocations, screw dislocations in this case by glide, we'll have something where yield stress of our material is more temperature dependent. And on the other hand, for FCC materials, we have strain hardening is more temperature dependent. So we can kind of draw what would happen with different crystal structures and what their strain curves would look like as we change temperature. Okay? So what I'm going to do is I'm going to draw two sets of stress strain curves. The one on the top is going to be FCC, and the one on the bottom is going to be BCC. Okay. So for FCC, we'll load up, we'll have plastic deformation and yielding. But as we reduce temperature, we're going to see not a huge change in our yield strength, but we'll see a change in that hardening type of behavior. Okay? So this is what happens as temperature goes down. Right? On the other hand, for BCC, we'll again see elastic loading, plasticity. We're going to see a big shift in the point at which our material yields, but not a large change in that slope afterwards. And so again, this is what happens as temperature goes down. So interestingly, when we have temperature, we're giving a little bit more of a boost or a kick, letting things happen a little bit faster. You could do the same thing by messing with the strain rate of your material. So this is functionally what happens when the strain rate goes up as well. Okay, so that's it for today. I posted some notes from Vaclav Vitek, who's a very well-known professor at University of Pennsylvania, and he's talking all about partial dislocations in these fractional dislocations in BCC materials along the screw dislocation. So if you're interested, please check that out. All right, so thanks, and I will see you guys when I get back from my trip. Take care.